So in the end, we've been buying seismic instruments for many, many years. And Willie Lee has been hammering on us for many, many years that we are not testing them. We just buy them and take it on blind faith that they work. So we finally decided we didn't want Willie hammering on us anymore, and we decided to really test them. Willie, of course, had an extensive testing program in Taiwan and discovered that instruments don't always meet specs. So we decided, well, we're going to try and follow his recommendations. So we went, when we received the prototypes, we went to Albuquerque. This is a real education for me. I didn't appreciate what really goes into not only just manufacturing of an instrument, but testing them. So I'm just going to show you a few slides of what was done. This is an old Russian shake table. It goes back and forth at 1 cycle per second and is very precise. You can measure, you can calibrate the instrument and indeed understand what it's doing. Here we go. This is a precision ground piece of granite, level to 4 microradians, and this is a slide that's controlled by a motor. You mount the instrument here, and it goes back and forth 40 centimeters. And so here's an example of what you record. This is time in seconds, and the instrument is accelerating, hits the end of it, goes back, and we start in the back direction, back and forth. You can integrate that to velocity, integrate that to displacement, and if you do this, and the instrument is doing what you want it to be doing, you'll recover that displacement of 40 centimeters, which you do. So it's a rather stringent test on the instrument. We had temperature specs that I didn't really go over, but we had a temperature chamber. You mount it on in the inside here, and you can rotate it. So here's temperature from minus. You know, your garage can get really hot in the summertime, at least in the Bay Area, and get really cold in the wintertime too. So the specs went from minus 30 to 0 degrees centigrade. It had to be within 2% accuracy, and from 0 to 30 degrees centigrade within 1%. We took various, at these red lines, we took various temperature measurements at various temperatures and made sure that it was compliant. This is just a spectrum of ambient noise for the 3 channels. Green is vertical, and these are, I'm sorry, green is the horizontal. The red is, I can't see it, vertical. And the other one is the other horizontal. So the way to look at this, this is 1/10 of a hertz here, 1 hertz, 10 hertz, 100 hertz. This is the low noise model. This is the best, quietest site that we typically record anywhere on the planet. This is what the noise is in Albuquerque, which is a very quiet site. You can only achieve this kind of noise if you have like a Streckheisen STS-1 with a very high-quality Quantera digitizer, or there are other companies that now make very good digitizers. So this is not that kind of instrument. This is to record strong motion in an urban area. This purple line here is what you would expect for an 18-bit instrument, like a K. Is actually not quite as good as a K2, and you can see we're slightly better than K2s, but then 18 bits, it's like 18, 19 bits between our specs of 1/10 and 30 hertz. This is a 3G clipping level. So this is, if you're familiar with instrumentation, it's like a K2. And I mentioned timing. We brought the instruments here in Menlo Park. We set them up just like you would have in your house. We had to go out over the internet trying to synchronize time. And then we disconnected the accelerometers. Gray did this test, and he put in a square wave pulse that was triggered by GPS. So it's very precise square wave. And we recorded it, and if you expand it, you can see the actual samples at 200 samples per second. This is at 22 hours 34 minutes when the pulse came in, and you can see the rising edge of the pulse is within a sample at 5/100ths of a second, 0.05 seconds, 0.05 seconds. Just to confirm that NTP timing is working. So in this case, we were getting better than 20 milliseconds. Here's a clipping test, the 3 channels. We bang the instrument, and you can see the 1 channel clips at 3G here. This is time. We wanted it to recover within 10 seconds. It actually recovered within 0.04 seconds. So that's encouraging. And we did other torture chamber tests, tilt tests, where we rotated it and looked for cross-axis contamination. And then finally, we did a test where we just said, okay, what would happen if the power disappeared during an earthquake? So these are the 3 channels. We didn't want to see transients where the power went off, and we didn't. Those tests were taken at these dashed lines. They were pretty quiet, but we did see things like this, where we saw noisy channels. It turns out this wasn't the data logger, but it was this Colibris sensor, and so the manufacturer's been going back to Colibris. GeoGIG's been working with Colibris to resolve these issues. So the instruments were extensively tested, and we didn't accept them until they met all the performance specs.